So what is my opinion on HTM? I read the book on intelligence that he wrote, and that was kind of the main ideas that he used to develop the HTM model. So HTM is basically a kind of hierarchical structure where you have a memory and a temporal relationship, and each stage in the data structure you're trying to predict your signal at the time step t+1, and you take the difference between your prediction and what you see at t+1, and you send that back up, and you try to use that to increase your prediction, and you do that in layers, and then try to improve the model this way, or the prediction this way. It's very interesting because it might be a reasonable way to do predictions, but so far I haven't seen any HTM model evaluated on the standard benchmarks. So I suppose that it's not as good as the LSTM model, for instance, or convolutional neural nets for computer vision.
Yes, you mentioned this Turing machine network. It's an LSTM. Is it published, this one? This one?
So the paper is published where you have the description, but I don't think there is any implementation available.
Yeah, and it's an LSTM too on the Turing machine?
For the neural Turing machines, I don't remember whether it's an LSTM or if it's just a regular net. No, it's an LSTM. Okay. Yes. Another question?
It's quite encouraging. I'm just curious about the application level of the networks, genetic algorithms. Are they out of the are they still being investigated?
So the question is, what about genetic algorithms? I remember in the beginning neural nets, some people used a genetic algorithm to try and evaluate the kind of architecture that were suitable for a specific task. But I'm not sure it's actually any useful anymore. And genetic algorithms, they are a really expensive method. For instance, if you have a loss function, if your objective function, if you have a derivative on that, it's much easier to do gradient descent, and you will get it's much more cheaper to get good results by doing gradient descent if your loss function is derivable. But sometimes it's not the case, and in that case you have to use meta-heuristic models like genetic algorithm. And it might also be useful when you have several conflicting objectives, like for instance performance versus cost. And for those kind of situations, genetic algorithms might still be interesting. But it's not deep learning at all. Yes?
Have you seen the recent article that said that deep neural networks are easily fooled? That you can produce images that humans definitely not classify as a given class, and the network give a very high confidence on this?
So yes,
what's your take on this? Yeah.
So there is a recently published paper that shows that you can make a neural net classify like a bunch of white noise as an ostrich or whatever, or stuff that looks like generated images that are artificial and not any kind of natural images, and you can classify them to arbitrary class. You can make the network believe that they are from arbitrary classes. So it's interesting because we don't really understand why it happens, so investing why is interesting. It might also be a possible problem for security reason if you deploy a computer vision system, if you can forge a specific input to hide stuff, for instance. But in practice, you still need to have access to the weights of the model to do so. So if you have secret weights, you cannot generate those kind of images without having access to the model. So I'm not sure it's that, and maybe the brain itself, you could, if you had access to the synapses connections, you could do the same on the human brain. So I'm not exactly sure whether or not it's how deep is it a problem. Other questions at the back. So are there any limits at things that network cannot do? So up until recently, neural nets were only useful when the input was a bunch of fixed size vector and the output fixed size also, like a class or a bunch of regression values to guess. They were also good at two-dimensional space input or three-dimensional and so on. And the main limitation was to adapt them to a variable length inputs, but this has been solved very recently. But we can imagine that there are other representation problems where the representation of the data doesn't really fit either as a fixed input size vector or a sequence of elements. So for those problems, I don't know any, but they might not work easily. And also, if you have higher level feature representations, for instance, if your data is already generated by humans that have some thought, judgment stored in an Excel table, for instance, and you don't have many examples, in that case, it's probably better to use other algorithms like random forest, for instance, because you don't have enough training data to train a big models like a big neural net without overfitting significantly. And furthermore, maybe the features are already high-level representations, so you don't really benefit from trying to extract higher-level representation because maybe it's already as good as you can get and the rest is just noise. So I don't know. But it can happen. One last question. Yes.
So maybe my question is a bit redundant because in the beginning you actually said in bold that there is no convex optimization in
yes.
networks and stuff like that. Do you think that because basically what people use gradient descent schemes which were like from the Stone Age of optimization and stuff like that, and it's essentially because you have cost functions which are not convex, and so you can't benefit from the tutorial of convex optimization algorithms. Essentially, you do that in big O of 1 on epsilon. Yeah. So essentially, gradient descent is quite slow. Do you think there are any people who are trying to actually have convexify these loss functions? Because if you convexify them, then maybe you could actually manage to have the optimization of the weights or whatever objects are in the beast, and I mean,
all right.
train them very fast.
So the question is about optimization. So the model are nonlinear. So the loss function that depends on the nonlinear activation of the model is itself nonlinear and non-convex. So there is no natural way to get a convex optimizer which is supposedly more efficient from a convergence rate point of view. It might be possible to reformulate it to a convex problem, but it's not necessarily going to be faster, or maybe you need to introduce many more parameters, or I don't know. And furthermore, the kind of problems that we deal with, even to evaluate the objective function, you need to go through the whole data set. So you need to do a bunch of computations just to compute one gradient, for instance. So in general, we don't do batch gradient descent, we do stochastic gradient descent because it's too expensive to compute the full gradient of the loss on the full data set. And you said that we are using just dummy gradient descent, but it's not true actually, because most of those models, they use momentum, which is kind of a Nesterov accelerated gradient descent. So it's not as bad as it seems, and furthermore, because of the fact that it's too expensive, we have to do stochastic gradient descent. So there is no trivial way to find a convex formulation of the problem that will be more efficient than that. But there is definitely room for improvements, because we know that, for instance, SGD with momentum gets stuck in saddle points. And there is ongoing research on getting better optimizers to work around those optimization difficulties.
Yeah, just a comment. If you actually happen to convexify the problem, if the convex formulation, just as the non-convex optimization, would benefit the same from the batch, stochastic, whatever. So that only says that even though you are not convex, you can still manage to make it fast, but it doesn't mean that the convex stuff wouldn't as much profit from it.
Okay. Yeah, maybe I don't know, but I think people have tried, and so far there's nothing. Let's wait.
All right. Thank you.
Just wanted to say that the slides are on speaker deck, and at the end you will find many references to papers if you're interested.